Welcome back to ChemDoctor, and this is the fifth video in the series on chemical kinetics. In the last video, I introduced the concept of rate law, and what we're going to do now in this video is start the process where we learn how to determine the rate law for a particular chemical reaction. And there are going to be two methods to approach this problem. In the first method that we're going to deal with here in this video, we use what's called initial rates and the ratio method to find the rate law for a chemical reaction. And in the second method that will be addressed later, we use the integrated rate law to carry out the same function. So the first thing is that we're going to look at the rate law for the reaction between bromide and hypochlorite, and we can write the proposed rate law down. So it will be rate is going to be equal to, and we'll have a rate constant. This is a small k. I know it looks like an R, so you know what, I'll label this. It's a small k, just to be clear about it, versus a large K, which it would be an equilibrium constant. So this is a small k. It is a rate constant in a rate law, and then this will be times the concentration of Br minus, and that will be raised to an x power, which is the order of reaction. That's the thing we'll be finding. And then this will be times OCl minus, and we'll raise this concentration to the y power. Right, where x and y are the order of reaction respectively for each of the concentrations. Another concept here that we're going to deal with is called the overall order of reaction, and the overall order will be the sum of x plus y. All right, now remember that in our lives right now that reaction order can be essentially one of three values. It can be actually any value, including fractional values, but for our purposes the reaction order can either be x equal to 0, okay, x equal to 1, or x equal to 2. And in the previous video I went through what each of these orders mean, and essentially a zero order reaction is one that is usually a catalyzed reaction. Order 1 is where the rate is directly proportional to concentration, and order 2 is where the rate of the reaction is proportional to the square of the concentration. So let's look at this table of data and figure out how we're going to find x and y. So if you look at this table of data, what does it represent? Okay, these are all initial rates. So the rate of the reaction at initial concentration of Br minus, if we look at experiment number 1, I'll go ahead and label these 1, 2, 3, and 4. So if we look at experiment number 1, what are we dealing with here? So we have the initial concentration of Br minus given in molarity as 0.12. We have an initial concentration of OCl minus at 0.18. And the rate of this reaction was already determined for us, and we're using initial rates kinetics. So what is that? So I scripted a little graph over here on the right that would show the decrease of the concentration of Br minus with time, which gives us the shape that we would expect. And if we're doing initial time kinetics, then we determined the slope of a tangent to the line, which was here, as close to t equals 0 as possible, and the slope of this line is in fact this rate. So what we've done in this experiment is the rate of reaction has been found for different initial concentrations of these respective reactants. And remember that we have, when you look at this, there are two reactants. So the challenge is to find the x and the y, the x being the order of the reaction for Br minus, the y being the order of reaction for OCl minus. So what we're going to do is we're going to use the ratio method. So we're going to take the ratio of one column of data to the other column of data, and we want to choose this ratio so that one of the data sets cancels out, and we're able to use simple arithmetic to find the order of the other reactants. So what we're going to do first is we're going to utilize experiment number 1 and experiment number 2, because in experiment number 1 and 2 you see that the rate, or excuse me, the concentration of OCl minus is constant, but the concentration of Br minus, the two different initial concentrations, two separate experiments, the concentration of Br minus was different. All right, so what I'm going to do is set up a ratio, and I'm going to do that so that the bigger value is on top. So I'm going to have the rate of experiment number 1 will be in the numerator of this fraction here. Underneath it will be the rate from experiment number 2. This will be equal to now another fraction, and in the top we'll have the equal, or excuse me, almost made a faux pas there. We're going to have the rate constant from the respective rate law of the reaction. All right, and on this, so on the right side of this equation, we're going to have the other side of the rate law. So we'll be using the Br minus times the OCl minus. Now for the Br minus in the top here, we're going to have 0.12, and this will be raised to the x power. In the bottom, we're going to have 0.06, and this will be raised to the x power. The same exponent because it's the same order of reaction, since this is for the Br minus. And then the OCl minus will be 0.18 raised to the y power, and the bottom will be also 0.18 raised to the y power. All right, now you can see what's going to happen here. Then the rate constants cancel out; they are the same value, and regardless of what y is, this quantity is identical to the one below it, so this cancels out as well. Now, when we go ahead and carry out the arithmetic, you see that on the left side of our equation that this ratio is equal to 2, and on this side the ratio inside the bracket also is 2 raised to the x power. Now, the only way that these two quantities could be equal is if x is equal to 1. So we have found the order of reaction for the Br minus. It's going to be 1. So now we're going to use the same trick for the OCl minus. And when you look at this, you can see there's a bit of a dilemma, because nowhere in the Br minus initial concentrations did the experimenter hold that constant. But that doesn't matter now, because we know what the order of reaction is for Br minus. So what we're going to do is we're going to look for the place where the concentration of the OCl minus changes, and for that what I'm going to do is I'm going to grab experiment number 2 and experiment number 3 right here. All right, because we go from an initial concentration of 0.18 to 0.019 in the third experiment. Remember, these are independent experiments. So let's go ahead, and we're going to set this one up exactly the same way. I'm going to put the larger value over the smaller one, so we're going to divide 0.0395, all right, by 0.00988. Okay, and then again, this is going to be equal to the right side of the equation, which is the other part of the rate law. Again, the rate constants, I'll put them in like this. They're going to be canceling out. Now, we need to be careful here. Our Br minus is going to be 0.06 in the top. All right, and in the bottom it will be 0.03. These are both raised to the first power. I'll put that in just to be very clear. And then The value for the OCl minus in the top will be 0.18. All right, raised to the y power, and in the bottom we're going to have 0.09, also raised to the y power. All right, so remember that quickly that the k's are going to cancel out. Now, this is going to be equal to, on the left side, to 4. All right, and 0.06 by 0.03 will be 2. And then the value that will be inside the bracket raised to the y power is also 2. So if I just bring this over here now, we're going to have 4 divided by 2 is equal to 2 raised to the y power. So 2 is equal to 2 raised to the y. So the y power for this is equal to 1. All right, so now we've established the rate law for the OCl minus. So now I can write the rate law. So the rate law is going to equal K times Br minus raised to the first power times the OCl minus also raised to the first power. The overall rate, or excuse me, the overall rate, the overall order, excuse me, will be 1 plus 1, and I'll write it out to be clear, which is equal to 2. That's the overall rate, or the overall order of the reaction. Now, we can find the rate constant using any column of data in here. So what I'm going to do is we'll use experiment number 4 for this. All right, and so the rate of experiment number 4 is 0.0791, and I'm going to put my units in now. So it's molarity per second. This will be equal to K. The value for the Br minus is 0.24, and that's in units of molarities, and then that's also raised to the first power. The concentration of OCl minus is 0.09. This is also raised to the first power, and let me get my molarity in there. And so my rate constant in this case is going to be equal to 3.66, and the units are going to be molarities to the -1 and seconds to the -1. Okay, and again, I used initial rates, the ratio method to find the order of this reaction, and with that I'm going to go ahead and close.